So it's a pleasure to give this seminar about, a topic that is dear to my heart, that is the antinucleosynthesis that we can study in the laboratory in hadronic collision at the LHC. And I would like to start with just setting a little bit the stage about why we do this and why we find it interesting. So antinucleosynthesis and what are its implications. So there are three main questions that Alice is contributing to address. The first one is a nuclear physics problem. So we have this very loosely bound object, like deuterons have a 2 MeV binding energy, hypertritons that are like objects where you have inside a proton, a neutron, and a lambda, even more loosely bound. If you have to imagine that to remove a lambda from this object, you only need 100 of keV. So you get this very loosely bound object produced in very violent collision with the LHC. Especially in the heavy ion collision, we think that there is the formation of quark-gluon plasma, the rapid expansion of a medium, and still, even going through all these, we have this very loosely bound object that are formed. This many people refer as like the snowball in hell puzzle. And of course, to address this, we have to study the production of anti-hypernuclei production at the LHC with extreme precision. Of course, this is not the only thing why we do this. I mentioned hypertriton, that is this bound state of nucleons and hyperons. And studying the properties of this kind of object really tell us something about the interaction among nuclei and hyperons. And in this respect, Alice delivered the most precise measurement of the properties of hypertriton. And I will also tell you more if we can extend this, and we can also get something new out of this and so on. But last but not least, it's not the only thing that we can do, like these first two bullets. The third bullet is something very recent that we are also starting in collaboration with people from Munich. Is like how we can use our antinuclei producing at the LHC to really interpret the flux of cosmic ray antinuclei. This is very important because there are several now experiments on satellites and on the International Space Station that also do like dark matter searches looking at the antinuclear flux. And this, of course, goes also beyond the study of antinuclear production that is anyway a key ingredient in this kind of interpretation of the cosmic ray flux of antinuclei. But we can also do at the LHC the study of the interaction of antinuclei with material, thanks to the fact that we really produce abundantly antinuclei. So I will start from the first point, so the study of the production of antinuclei at the LHC. And I usually like to start with setting a little bit the stage, telling you about the two principal models that are used to interpret the antinucleosynthesis at collider. As I said, this is kind of a puzzling because it's a very loosely bound object, yet we have two models that manage to give quite good predictions about what to expect in this kind of collision. So the first class of models are the so-called thermal models or statistical hadronization model. I'm sorry, you will see in this talk, I will use the two terms interchangeably, but they mean essentially the same thing in my mind. So in the thermal model class and statistical hadronization class, hadrons are emitted from the interaction region. So you have the collision, and you have the emission of hadron. And what is actually assumed is a statistical equilibrium. Essentially, the system reaches a limiting temperature after which you don't change anymore the abundances, the relative abundances of different particles. So the ratio of the different abundances is actually driven by the key parameter that is the temperature. The absolute abundances also depend on the volume, of course. And the expression that we usually have is the key expression is actually a bit more complicated, but for larger masses, what you get is essentially an exponential that is dependent on the mass of the object and on the temperature of the chemical result. And of course, for nuclei, where we have a very large mass, we really have a strong dependence on the temperature of the chemical result. So the nuclei are really a good thermometer of the collision in this model. So this kind of models are mainly used to lead. In the following, I show you that this can be extended also to PP collision and P-lead collision. But here on the right, you essentially see the yield per 1 million of events as a function of square root of S. And you see the LHC fits in these two blue lines, 2.76 TeV, 5 TeV. I know that some of you work in the STAR experiment, so you also then explore lower energy. But there is let me just point out one of the features of this model. One key prediction of this model is at the energy of the LHC. You see that there is a dashed line and the continuous line. For the continuous line is for nuclei, the dashed line is for antinuclei. You see that the dashed line approaches the solid line at the energy of the LHC. So at the LHC, we really expect the same abundances of nuclei and antinuclei, more or less. I will tell you more about this later. The second class of models is the coalescence model. Here I will simplify a bit. I mean, it's really more complicated. It's a really fascinating math also behind the most modern version of the coalescence model. But essentially, you have your collision, you have protons and neutrons formed in the collision, and this is they are close in phase space. Essentially, they have certain probability of forming an antinucleus. If you have a proton and a neutron, can form a deuteron, and of course, the more you add nucleons, the more you have the probability of forming other nuclei. Of course, this tell you that already in the coalescence, we have an interplay between the configuration of nucleons produced in the collision, so in the phase space of the collision, and the wave function of the nucleus that is formed. Of course, these two models give really very quantitative prediction in high energy collision, and we can test them. And this is all about the ALICE experiment that I will now introduce briefly. So, okay, many of you might know it. I mean, this is the sketch of the ALICE experiment. This is actually already a sketch including the run 3 configuration of detector. For the research of antinuclei, essentially what we need mostly are 4 different systems that are the inner tracking system, the time projection chamber, the time of flight, and the trigger detector that are the V0s. So essentially, to identify nuclei, we use 2 different techniques. The first one is the study of the specific energy loss in the time projection chamber, the TPC. And here you see on the top right, the specific energy loss in the time projection chamber as a function of particle rigidity. So you see on the right of this plot, you see all the particles, and on the left, if you want, you see all the antiparticles. And you see very clearly the bands of helium-3, deuterons, and anti-deuterons, anti-helium-3 here. So essentially, for Z equal 2 nuclei, so anti-helium-2 and anti-helium-3, this already provides quite very good PID, but for Z equal 1, so single charged nuclei, you see that for this very good only at low momentum, where with the precision of 6.5%, you can really distinguish these particles from the other light level nuclei. Going to higher momenta, you need also the time of flight detector. Here you see the beta, so the speed of the particle is a function of the momentum for different particles, and essentially the top is the stopwatch that measures the time of flight of each particle. 65 picosecond is the precision in the collision, and the 20 picosecond is the precision of our time of flight measurements in PP collisions. And essentially here you see that you can very well separate all different particle species. And in particular, you see the deuteron, you can clearly separate essentially up to 6-7 GeV/c. So here you see what you do when you combine time of flight, then the X momentum from the tracking. You get a very nice mass spectrum measured through the time of flight, and this is essentially the signal extraction you can do to get like the abundances of different antinuclei. And when you analyze different momentum classes, momentum slices of all these, you get all the particle spectra. And here you see, I want to show you, essentially, we have the example of proton-proton collision at 13 TeV. We have even a more recent paper where we have high multiplicity proton-proton collision, and I will show you the result about that later. And on the right, you see actually the case of p-lead collision. We have measurement in lead-lead collision, xenon-xenon collision. You know where I'm going with this. Essentially, all the collision system where we add collisions in at the LHC, we essentially made these kind of measurements because we really want to characterize what is the kind of production mechanism that is behind the production of nuclei. So first thing one wants to investigate, I mean, I told you before when I showed you the plot of the thermal model prediction is that thermal model predicts that the yields of antiparticles and particles at the LHC energy in lead-lead collision is essentially the same. So this is actually, you see, so for thermal model, you can write down the formula for essentially protons down to all nuclei. In the case of coalescence model, you get the nucleons as an input. And then actually the funny thing is that for heavier nuclei, you actually get the same kind of prediction. So this kind of observable is not really sensitive at the difference between statistical ionization and coalescence. Still, it's very important to check that even this very fundamental prediction is correct for both models. So here you see essentially the antiproton over proton ratio in lead-lead collision for different centrality classes, essentially different overlap of the nuclei that are colliding. And you see that essentially this in this case we get a lot of protons. You have to imagine that in a central lead-lead collision we get 40 protons and 40 antiprotons. This means that the uncertainty you actually see here are just the uncorrelated systematic uncertainty. The systematic uncertainty are essentially not present, and you see that the antiproton over proton ratio is essentially around 99%. And you see that for the anti-helium-3 over helium-3 ratio, and here this is shown on the right slide, on the right part, on the right plot here, actually this ratio is a little bit below, it's around 95%. This is actually something that we expect, so because when we have like antinucleos over nucleos, we expect that this goes as like antiproton over proton to the power of the number of nucleons we have inside the nucleus. Of course, the formula is a little bit more complicated than that, but essentially these tell us, these two measurements tell us that at the LHC, the quantity of matter and antimatter that are produced are essentially the same. So we have the same abundances of matter and antimatter produced at mid-rapidity. So that simple formula, one can actually then study it in a little bit more detail in the grand canonical ensemble statistical ionization model, so the thermal model that I was explaining you before. And if you measure, like we did, like proton, antiproton, helium-3 over anti-helium-3 over helium-3, anti-hypertriton over hypertriton, and so on. So all anti-hadron over hadron ratio, you can then fit this kind of expression that you get from the thermal model and get one of the key parameters of that tell us what is the baryon density at the LHC, so the biochemical potential. So in this slide, essentially, I'll show you the biochemical potential as a function of the number of participants in the collision, that is a proxy, that is essentially the centrality of the collision. You see here the dashed line is what was got, what the latest statistical organization model fit from a Nature paper got for the mu-B at the LHC. So you see this huge band that essentially dominates the scale of the plot. And actually you see that measurement from Alice now really nailed down the biochemical potential at a level that is less than 1 MeV at the LHC. So essentially, we really are in the regime where we get very, very close to what we expect to be the start of the universe. So, of course, this was to check one of the key predictions of the thermal model, so the different abundances, also to fix one parameter in the thermal model, the biochemical potential. But what we are really interested is to understand if the thermal model or coalescence are correct. So to do this, we can study different kind of observable. One of these is the ratio of the number of neutrons produced over the number of protons produced in the collision as a function of centrality. Essentially, here you see all the collection of different measurements that Alice did. So from proton going from p-lead to lead-lead collisions. And here you see essentially that we have a problem. So both coalescence model, that is this green line, and the thermal model that is actually the thermal model is sitting essentially between this dashed black line and the solid black line. They actually qualitatively describe quite well the trend. If you get like a thermal model with a specific correlation volume that tells you essentially in the canonical version of the thermal model the unit of rapidity over which the quantum numbers are conserved. If you take an intermediate configuration, let's say 1.6 unit of rapidity for this conservation volume, you actually have a very good description of the data. So we are a little bit in trouble because we see that in this case, in this observable, we are actually not so much sensitive to the difference between coalescence and thermal model because they are really close. And you see the uncertainty we have, they will get better, and we already have better measurement that will come up very soon. But still, it's very difficult to get uncertainty down at the level that you can really discriminate between these two models. One thing that we have to observe, though, is that to describe this neutron over proton ratio with a thermal model, we need this volume of 1.6 unit of rapidity, while to describe something like the proton over pion ratio here, actually this is an odd version of the model, these red curves, but it's what we actually published. You see that actually you need something like 5-6 unit of rapidity. So in the thermal model, we have a kind of internal inconsistency in the description of nuclei sector and proton and light level sector. But this is still something that has to be worked out by the theoretician, or might still mean that we have out of equilibrium production at low multiplicity. So maybe the thermal model is actually not working in the regime of proton-proton and p-lead collision. But of course, we can further this kind of investigation. So actually here, I forgot there is a link to a talk, but you actually can go and see, it's a talk in the quark matter from Shoav Kundu, that is one of my colleagues here at CERN, that actually we did the analysis together about this, the event by event fluctuation of nuclei production. Essentially, what you look is not anymore only at the average number of nuclei that are produced in the event, but you also look essentially at the shape of the distribution of the number of nuclei that are produced. But here you can focus on antideutrons because are particularly pure. You don't have contamination from knockout from material and so on. And you can study the kappa 2 over kappa 1, essentially the variance over the mean ratio as a function of centrality. And if you do so, if you study the variance of your distribution over the mean of the distribution, in this case, you see that we are sensitive to a difference between a very simple coalescence model and the thermal model. The thermal model always foresee a kind of Poissonian distribution. This essentially means that kappa 2 over kappa 1, so variance over mean is equal to 1. Well, for the coalescence model, you have kappa 2 over kappa 1 that is very different from 1. You should not stop here. actually in the investigation, if you are able to do even by event fluctuation analysis, you can even study the correlation even by event from the number of proton and number of deuterons. Essentially, you investigate how the population of deuterons, of antideuterons, is modified once you measure a certain number of antiprotons. And so this is the very simple Pearson correlation coefficient that you can measure, again, as a function of centrality. The interesting thing is that while kappa 2 over kappa 1 is not sensitive to this correlation volume in the statistical hadronization, the correlation it is very sensitive to this. So what we did is we measured the correlation between antiproton and antideuteron as a function of centrality, and then we fitted the statistical hadronization model, and essentially what we got is again 1.6, a correlation volume that is 1.6 unit of rapidity. So it's consistent with what we saw with the yields of antideuteron of deuteron over protons. But again, we have still a problem to compare with the antiproton Nielsen fluctuation. We are in contact with theories. There are ideas, but still, there is some homework for model maker here to figure out really what's happening. But okay, we also know that coalescence is not really dead, right? Because we still have the problem that even though we have this kind of good description of nuclei yielding in lead-lead collision, in proton-proton collision, this is really not the case. We really have some struggle, and we still have a few things that we can investigate. So what we usually do to investigate the coalescence parameter, the coalescence model, is to compute the coalescence parameter. So in this case, okay, I will simplify it because it's always, you see, this formula, at least to me, when I started, it was really confusing. Essentially, you just divide the spectra of your nucleus, scaled by the momentum, you scale just the momentum by the number of nucleons you have inside of your nucleus, and you divide the spectra with the momentum scaled by essentially n times so the proton spectrum at the power of a. So in this case, you see the B2 for deuterons on the right, the full formula you see here on the left, but also, to drive a little bit, I want to just drive your attention to the main feature of this kind of parameter is that, so the larger is this parameter, it means the larger is the coalescence probability. So the more we get protons, we get nuclei starting from the same population of nucleons. So, as I was mentioning before at the beginning, so this model is sensitive to the configuration in the phase space, and so what we see is that in small systems we have a small distance in space. So only momentum correlation matters. So if we have the two nucleons pointing in the same direction, we expect to see a nucleus being formed. So we expect a larger coalescence parameter in small system. In larger system, we don't have only the momentum correlation matter, but also the space correlation matter. I know that Laura Fabietti did a colloquium here, and I think she also explained that you can also quantify this kind of effect with correlation functions in femtoscopy measurements, and indeed there is a very tight connection with this, and I will also come to that later. But to just show you an example of what I mean, essentially here you see the coalescence parameter as a function of charged particles, and you see on the left is you see essentially the proton-proton collision that have a larger coalescence parameter, and indeed in lead-lead collision you see that this coalescence parameter goes down. So this is really an hint though of the fact that whatever production mechanism we have, this is a production mechanism that is aware of the size of the system. The only thing that we don't know is that coalescence model is not only aware of the size of the system, but is also aware of the size of the object. So, and actually here you see that this parametrization from the coalescence model, these black and red dashed lines that essentially comes from a paper of Alexander Calvite and Francesca Bellini that I point out here. And you see that what we have here, we have a bit of a difficulty of interpreting all the BA measurements with the same parametrization of the radius. Essentially, if we use a parametrization that is based on the measurement of HBT radii in proton-proton collision, we really see that we can describe the data in proton-proton and P-led collision and even peripheral lead collision. Unfortunately, this dashed line, that is the parametrization that is fitted to this HBT radii, so the correlation that Laura was mentioning in the other colloquium, this parametrization breaks down in lead-lead collision. There, you really see in central lead-lead collision, you see that the measurement goes down. So what can we do? So we can really then restrict ourselves in proton-proton collision, where we really have very good measurement of the radii of the source, and we can study a very well-known nucleus, that is the deuteron nucleus, and then we can really have a look at what is the relationship between the nucleus wave function and the size of the system computed with a correlation. So this is a development, a theoretical development that was pioneered by Kiefer-Bloom, and that we also, to some extent, I contributed to refine. So we have a recent paper on PRC where essentially we exemplify this kind of formalism. And what you see here is in the recent paper of Alice is the B2 as a function of momentum, compared with the coalescence prediction that are based on this formula. Essentially, we have the correlation radius that is taken from Alice's measurement of the correlation radius, and the Wigner density that is essentially taken from different wave functions of the deuterons. In this case, you see different wave functions and how these adapt to our measurement. What you see is that it's a bit disappointing on one end, and it's actually expecting on the other. So it's a bit disappointing because you see that the Gaussian wave function, that is, we know from electron deuteron scattering, that is not the proper wave function of the deuteron, is the one that really fits best our data. Even though, okay, always with the same RMS radius of the deuterons. However, you see that the more accurate parametrization, like the Ulten or the chiral effective field theory parametrization of the wave function of the deuteron, actually are factor 2 off. So we know in this coalescence approach, we have some very rough approximation. I invite you to read the paper where there is an example of few of them. And so this is kind of expected. So on one end, it's disappointing because we don't get it right in the first trial, but on the other end, we know that we have approximation in this kind of formula that can really account for this kind of discrepancy. So when we have this kind of situation where essentially we have just factor 2 of precision of the model, we cannot really go and investigate the deuterons and so on. So we really have to move to something where we get a really large impact of the wave function on our prediction. And this is actually the hypertriton. In the case of hypertriton, we know that hypertriton from the lambda separation energy should have a radius of approximately 10 Fermi. And this means that if coalescence is right, even with this factor 2 of uncertainty on the coalescence predictions, you still have a very different yield of hypertriton foreseen with respect to the statistical hadronization model. Here you see statistical hadronization model. Here is in the black and dashed line, and the coalescence models are this blue curve, and you see there is this huge difference between the two models. And so if we go and do the measurement in small systems like we did, we really can distinguish between these two models, even though like the coalescence model has a large uncertainty given by like some assumption that you have inside there. This is still not enough to cover the difference with respect to the statistical hadronization model. So essentially what you see is that you have a tension with a statistical hadronization model if we look at our proton-proton and P-lead measurement of hypertriton production. And for configuration with larger correlation volume, this is essentially these are essentially almost excluded. And to really explain this, you really need a small correlation volume in the statistical hadronization model, while the two-body coalescence essentially agrees with our data, assuming a very large hypertriton radius. So this brings me to the hypertriton chapter of the presentation. It will be faster, I promise. So as I showed you, we measure hypertriton in PP and P-lead collision. However, you saw the error bands were very large because the production is very rare there. We're talking one every, let's say, 10 million events. So it's really, really rare. In lead-lead collision, we get many more. And actually, so just to set a little bit the stage, so many of you know, and I already told you, hypertriton is proton-neutron lambda state. Essentially, theorists see it as like a deuteron lambda bound state. So almost an allonucleus with a lifetime that is very close to the lifetime of the lambda, and the lambda separation energy that is of 100 keV. So what is interesting is that so we had many measurements in the history that were really confirming this kind of picture, but with very large uncertainties. And then we had like the era of heavy ion collision, where like a star collaboration pioneered this, where you really see that you have the production of hypertriton in heavy ion collision. You can study the properties there. And there you see we had hints of like smaller lifetime, larger lambda separation energy. We still have some large uncertainties, and Alice can really give some very precise measurements in this area. So how do we measure hypertriton? Essentially, we have like what we do is we look at the helium-3 pion decay. So we have the hypertriton decays in helium-3 pion, and essentially identify the helium-3, we attach a pion, reconstruct the secondary vertex, and we train a machine learning discriminator such that we get this very nice signal over background. So we really have very clear identification of hypertriton, and this allows us to essentially extract very clean lifetime CT spectrum, for which we can get the lifetime. So this was already done with the first run of lead-lead data taking we had in run 2 of the LHC, with the first data set of lead-lead we had in run 2 of the LHC. That is already published, and you see here the measurement. The previous measurement is actually the one from star collaboration. The science paper here is again star collaboration. Of course, the new lead-lead data sample in 2018 is actually much more precise because we collect much more data, and also we use, thanks to the usage of these machine learning methods. And so you see that a single measurement has the same relative error as the world average. This plot has to be updated. Now we have also a new measurement from the star collaboration that is also very close to this Alice measurement. They did it in the beam energy scan. And actually, yeah, this allows us to test different predictions from the model on the hypertriton structure and final state interaction. But we can, of course, go on and also have a look at the mass of hypertriton itself. And this is actually what you see here. So the measurement of the mass of hypertriton as a function of CT. And from the mass of hypertriton, we can extend the binding energy. In particular, we are interested in the lambda separation energy. And the ALICE preliminary measurement here is shown in this plot, in this time series. And you see that essentially we see something that is extremely close to zero, compatible with zero. So these results are preliminary things. So why? Because we were really like nailing down this systematic setting. I can anticipate you that the paper will be coming in the next few weeks, unfortunately not for the main conference on hypernuclei, but in that paper we will have a smaller systematic uncertainty, and then you will see what are the conclusions. Essentially, I can already tell you the point doesn't move so much in the B lambda, actually doesn't move at all, and not even not the lifetime, not the B lambda, but the uncertainty really shrinks quite a lot. Last chapter is the one on the how we can use antinucleosynthesis to understand the search for dark matter in two secondary antinuclei that we observe in the cosmic ray fluxes. So essentially, in space, what we think is that the processes that happen are very similar to the one in the laboratory. So you have like primary cosmic rays that can be protons, that can be electrons, or like deuterons and so on, that impact on like interstellar medium and then create some kind of also antinuclei in the process. Of course, these kind of processes are extremely rare, as I already showed you. I mean, it's like nuclei are kind of rare at the LHC, antinuclei are rare at the LHC energies. And you have to imagine that the typical energy of the collision is of cosmic rays is we are of the order of tens of GeV of energy in the center of mass, while at the LHC we are the TeV energy scale. The thing is that some theoreticians think that it's not only these ordinary processes like cosmic ray proton, cosmic ray nucleus that create on interstellar media that create antinuclei, but actually the antinuclei formation is announced when we look at the collisions of dark matter particles like neutralinos and things like this. So this is a long-standing prediction. The first paper was actually in 1999. It's actually from a colleague from Torino. Yeah, the issue is that of course, to understand this, you have to have under control many ingredients. The first of which is what I talked to you about in the first part of the presentation. So what is the main background? So like the production of antinuclei in ordinary standard model collisions. And the second one is actually very, very interesting, is also like, what is the probability of the propagation of an antinucleus in all the universe, okay? So what is the probability that an antinucleus producing such collisions, so both the standard model collision and the dark matter collisions, what is the probability these antinuclei come to AMS that is very close to the atmosphere, or other experiments that will start also looking there? So to do that, we have to study what are the interaction of antinuclei with matter. This, of course, it's a little bit difficult at the accelerator, because, as we said, antimatter is rare to be produced. So what we do in ALICE is we study the difference of the propagation of antinuclei and nuclei in our detector. So for antinuclei, we know that we have a larger inelastic component of the interaction. So we know that we effectively observe less before we correct for the efficiency. Knowing very well what is the material inside of the ALICE experiment, we can really then gauge what is the cross-section of the absorption of these antinuclei. So this is essentially what you see. If we look at the number of antiprotons and divided by the number of protons detected in our experiment without correcting for efficiency, we see essentially this. We see that we observe less antiprotons because we get more antiproton absorbed in our detector. Of course, these the antiproton cross sections are known very well and are very well implemented in Monte Carlo like GEM4. So essentially, if you look at what is the prediction of GEM4 for this kind of ratio, you see that it's essentially predicting what we observe in the data. Now, of course, you see also a gap in this kind of distribution, and this is due to the fact that at low momentum, as I was explaining before, we only use the TPC to identify particles, so the particles cross less material, but at large momentum, we need like the TOF to identify particles, and then means that particles cross our transition radiation detector, that you can approximate it as large block of aluminum, essentially. So it's something that really blocks a lot of particles, and here you see that there is this huge gap in the ratio that you have. And again, I mean, GEM4 really reproduces very well because we have very good control also on the material, of the order of 5%, actually. We have a 5% precision on the material of TRD. So if we look at the antideuteron pictures of antideuteron over deuteron, you see immediately again the same kind of structure that we saw in antiproton over proton. What you see is that the GEM4 Monte Carlo actually doesn't reproduce so well the data. So what we did as very simple is we scaled the antiproton, the antideuteron cross-section in GEM4, because we know that the deuteron is cross-section is also very well reproduced, up to the point where we actually reproduce our data. And by doing so, we can extract actually the cross-section of the antideuteron in our material. So the first thing we did is actually to do the antiproton cross-section, because as I said, the antiproton cross-section is very well known, and we wanted to gauge our method with something that is very well known. And essentially what you see here in this plot is the sigma inelastic of our antiprotons as a function of momentum compared to the GEM4 parametrization that is essentially tuned on the unknown cross-sections. And you see that our measurements that is reported here with 1 sigma and 2 sigma confidence span, you see that this is actually reproduce the GEM4, the GEM4 parametrization that is based on measurement. So if we do the same for antideuterons, you actually see that this is not the case. So in the case of antideuterons, we get a systematic shift of our measurement, and we are able then to post the first measurement of antideuteron inelastic cross-section at low momentum. There was only 1 point at 10 GeV, and it was performed more than almost 50 years ago. Now we can really add this to the game, to the study of antinuclear interaction. But we can even go even lower if we extend our measurement to the region where we only do the measurement with the TPC. So this is extremely valuable, we say, both for astroparticle physics, but also for ourselves, because this is a direct input we put in our GEAN code to correct for the efficiency of detecting particles. So it's very important that we really have this under control, such that we understand what we're going to measure also in the future. But we didn't stop to antideuterons. We also, with the same kind of method, we also measured the anti-helium-3 interaction cross-section. And this is really a first. For antideuterons, we had this high momentum point. For anti-helium-3, we didn't have any kind of measurement. This was recently posted on the archive and submitted to Nature Physics. Here on the left, you see essentially the measurement using TPC only, and on the right is the measurement using the TOF detector. So what do we do with this? I'm almost at the end of the talk. We take all these kind of measurements and we do a simple exercise. We take a standard code for cosmic ray transport. We modify the inelastic cross-section of the antinuclei following the Alice measurement. And then we check what is the impact on the expected flux of antinuclei. So here you see the expected flux essentially above the Earth atmosphere for anti-helium-3. It was used a very simple model for the neutrino annihilation in 2 Ws that then hadronize in anti-helium-3 plus whatever. And you see that so essentially the signal peaks here at low transverse moment, at low energy of the helium-3. And this is the energy where actually you see here you see reported in the panel below the difference with respect to assuming no absorption of the anti-helium. So you see essentially that we have a 50% absorption of anti-helium-3 from the galaxy, and you also see the difference with respect to the blue band is actually what happens to the background with respect to the signal. So what you see is that essentially our measurements for the first time really allow us to tell for sure that we can see some of these antinuclei if they are there. Unfortunately, you see that also that the sensitivities of AMS is actually quite lower, but these also quite not enriched with the expected fluxes, but also this depends on the dark matter model and the dark matter hadronization. So to summarize, so we have very great progress in the field of antinuclei in energy physics in the recent years. We are now really pinning down the different models at the level that we really are working out the details of them, even going to the event-by-event description of the collision. We have very precise measurement on the hypertriton ID card, so all the properties. And of course, we don't stop here, but we go also beyond production cross-section and properties of hypertriton, but we also look at things that have an impact to actually the astrophysics community. And in the next years, what we want to do is to extend this program to A = 4, so even heavier hypernuclei and heavier nuclei. For instance, we want also to do like the absorption cross-section for anti-alphas, so anti-helium-4, and have a look there to if we see any surprises. And we want to extend our measurement to A = 4 hypernuclei, even though our colleagues on CERN Week, they also already started there quite recently. And the last thing I want to also mention, to me, what is really important now, I mentioned U lifetime and the lambda for hypertriton. So what is really important also for me now is that we see both, also we saw it also from STAR. The reason is that another parameter that is very important for to understand the hypertriton is like the different branching ratios to different decay channels. This is unfortunately very difficult to do because of backgrounds of correlated background of deuterons and lambdas. Also, well, this was observed first in the 70s. This is the reason why Alice doesn't have a paper out with that. Now also STAR collaboration sees and acknowledges this very huge background, and they came out with a version with a method to deal with it. Our method is to perform the measurement of hypernuclei in PP collisions, studying also the three-body decay. I mentioned this because I think this will be one of the highlights of what we will do in run 3, and it's also a project that I've been working with people in the audience today. So that's it. Thanks a lot.